In the last part of this lesson, what we wish to do is extend the concept of linear independence to functions. In other words, we want to develop a test for linear independence when we're looking at a list of functions. And the way that we can do that is by using what's called the Wronskian. So let's start with a list of functions, f0 of x, f1 of x, up to some n. And these are going to be real valued functions. And we'll do this on some interval AB. And what we want is a similar understanding for what linear independence meant for us before. We just have some functions in the place of what we would typically have as vectors. So if there exists scalars a0 through an such that a0 times f0 of x plus all the way up to an f sub n of x is equal to 0 for all x in the interval AB that we've specified, then the set of functions is linearly independent. When the only solution is the trivial solution. If, on the other hand, there exist scalars a0 to an that are not all 0, such that we can make this particular statement true, then we would say the set of functions is linearly dependent. So again, what we're looking for linear independence in concept is the same as what we had before. We want the only solution to be the trivial solution. Otherwise, our set is linearly dependent. The trick is coming up with a test, and that's where this Wronskian comes into play. So we have to have some particular conditions hold true. Let's see what those are. So f sub I, so one of our functions, so each one of our functions is sufficiently differentiable then we can find a bunch of derivatives. Particularly the ith derivative for each of our functions. So we take our equation from above, this one, and we start differentiating that equation a bunch of times. And what we get is something that becomes a nice matrix that we can then use as a tool. So let's finish writing out this statement. A sub n, f sub n, here's the ith derivative. And again, that's equal to 0. And we can do this. We need to be able to do this for 1 less than or equal to I less than or equal to n. So what this is saying is that our functions have to be differentiable enough to where we can generate what will ultimately be a square matrix. So then we create a matrix from a system of equations in the following way. So we have f0 of x, f1 of x, all the way up to fn of x for the first row. And then here we're going to have the first derivative of f0, first derivative of f1, first derivative of fn. Here we would have then the second derivative of f0, second derivative of f1, second derivative of f sub n of x. And then you just keep going, taking successive derivatives all the way up to the nth derivative. So this is going to be the nth derivative of f0, the nth derivative of f1, and then the nth derivative of fn. So again, you can see that we have to be able to find the nth derivative when we have n functions that we're working with. So those represent, in some regard, the coefficients, a1. So then we multiply that by our unknown coefficients, a1, a2, a sub n, and we want that to be equal to the 0 vector. So this is how we can create this system of equations by taking successive derivatives. Again, all we're really doing is just taking n derivatives of this function, or this equation rather, right here, and then turning it into its matrix form. This thing then, right here, is what we call the Wronskian. And that's this tool that's going to help us figure out whether or not we have a linearly independent set. So if there is a point x0 in AB such that the determinant of the Wronskian at that point is non-zero, then that means that the Wronskian is non-singular at that particular point. And it works out then that the set of functions is linearly independent. So we're using our test about the determinant being non-zero to interpret that as non-singular. And then non-singular, we then extend to linear independence for the particular functions we're looking at. So we do want to make a couple of notes here. Let's write this out. So if there is a point, we only need one, x0, in our specified interval AB, such that the determinant of the Wronskian is non-zero, then the Wronskian is non-singular. At x equals x0. And then again, our conclusion is so that the set of functions would then be linearly independent. And it's also really important to note that we don't get the reverse statement. In other words, we want to make sure that we don't make a false assumption. The determinant here of the Wronskian of x being equal to 0 does not imply linear dependence. Unfortunately, we would like to be able to make that conclusion. All we can do here is use this as a tool to prove linear independence. We cannot show that something is linearly dependent. That would require extra work. So let's look at an example of this. So I'm going to take three functions, e to the x, e to the 2x, and e to the 3x. And we're going to do this on the interval from -1 to 1. And what we're after here is, again, to show that these functions are linearly independent. The Wronskian itself is all that we really need. So the first row in the Wronskian comes from taking our functions as they are, e to the x, e to the 2x, e to the 3x. The second row comes from taking the first derivative of each of our functions, which would look like e to the x, 2e to the 2x, and 3e to the 3x. The third row would be the next derivative, the second derivative here, which would be e to the x, 4e to the 2x, and then 9e to the 3x. So there's our Wronskian. We'll go ahead and compute the determinant of our Wronskian now. And there's kind of some shortcuts to this. A little bit of a trick is noting that e to the x is common for each of our columns or rows for that matter. And if we want the determinant of this particular matrix, we know that we can factor out common factors. So I can pull an e to the x out of each of these, and we would have something like the determinant of our Wronskian being equal to e to the x times e to the x times e to the x times the remaining matrix. 1, 1, 1, 1, 2, 4, 1, 3, 9. And this is just a little bit of a trick in this one. We note that if I were to try and compute the determinant before factoring those out, we could certainly do it, but we get a lot of functions in there, and of course we would have to do this by hand because we can't just put this into octave and have a solution. The good news is, because e to the x is common everywhere, I can pull it out in front, and what remains is something that can be computed in terms of a determinant using octave. And because that is a determinant, we should probably make those look like determinant bars using the verticals. Okay, so let's get the determinant of that matrix, which is 2. So now we have the determinant. So this is equal to 2. We have the determinant of the Wronskian as a function of x is going to be e to the x times e to the x times e to the x, or e to the 3x, times 2. So let's just rewrite that, 2e to the 3x, in a nice clean way. So there's the determinant of the Wronskian. What we need to have is that there exists some point x0 on our interval. So here's the interval that we're working on. So some point in there for which the determinant of the Wronskian is non-zero, and then we get that this is a linearly independent set. So in fact, that's true all the time, regardless of the interval that I'm actually on. This particular function, e to the x, we recognize is never equal to 0 in this scenario. So we have something that's always non-zero. So for all values of x, we could say then that these three functions are in fact linearly independent from each other. So e to the x, e to the 2x, and e to the 3x are linearly independent. And there's our conclusion.